Right, Richard again here from Electric Classic Cars, and in this week's episode, sponsored by Mauser Electronics and TE Connectivity, we brought Bug Zapper to a top secret Aerodynamics facility just off the A361 near Daventry, called Catesby Tunnel, where hopefully today we're going to find out how we can improve the aerodynamics of that. Right, so we've come inside now and we've met the man, John. And John, you're going to have to tell the audience out there a little bit about Catesby and where we actually are. So over to you.
Yeah, nice to meet you. So we're here at Catesby Tunnel today, so the world's longest indoor test facility. Yeah. And we're here to scan your car. So we're going to get it in the workshop. We're going to take it to pieces. We're going to scan it so that we can do some aerodynamic development for you.
I just want to set the realistic bar very low. Remember, it's a VW Beetle. Aerodynamics and VW Beetles don't go well together, so I'm not expecting it to be very performant today, but I'm interested to see how the guys get on.
It's not about where we are now, it's about how much better we can make it. So everything is incremental steps. So we might have a brick, but we can have a slightly better brick by the end of it.
Well, I'll replace the word might by definitely. So, right, can we have a look inside?
Yeah, let's take you through.
Cool. Right, so we've come inside. The guys are really quickly cracking on with the car in the background here, but tell us a little bit about where we are and some of the history, because this is a really cool place.
It is. So what we've done is we've taken an old Victorian railway tunnel and we've tried to convert it into an underground test facility. So the problem when you test your car outside is there's a bit of rain, there's a bit of wind, there's another vehicle, and they all make a bit of noise to your test. Yeah. So we want to do an experiment that's the same every single time. Right. So by putting it inside, sealing the doors, the temperature's the same, we get the same test each time. Yeah. So we can test your vehicle performance and make incremental changes and then hopefully make it better.
You make it sound so easy, but I bet it wasn't easy taking a Victorian railway tunnel and turning it into a high-end facility that F1 companies can use, really. So
yeah, absolutely. So the tunnel looked like this when we looked to try and buy it in 2014. So they ripped up the track, they'd taken away all the road, all the rails and the ballast, and the drainage was destroyed. So we've had to start from scratch effectively, re-put in all the facilities, make the place dry, and then we've put in a super flat road.
How flat?
So it's within plus or minus 1 or 2 mil from being planar over 2.5 kilometres.
What? How on earth do they get a road that flat? It sounds insane. That's impossible.
It was a big ask, but effectively there's a concrete plinth's been laid across 2.5 kilometres. Yeah. That was then planed off with a laser guided planing machine and then paved with a custom paving machine. Wow. Starting at the far end, continuously laid all the way back up this way.
That's insane. So now the tunnel has been completely reborn. I can see some of the photos of it, back in the day. And now all of this with the building works has made essentially a absolutely mirror flat tarmac for how long?
It's 2.5 kilometres.
Yeah. 2.5 kilometres. Yeah. Can we have a look at it?
Let's have a look.
Oh, cool. Right, John, this is really cool. This is like a Bond layer, the Bond villain's layer, isn't it? What you need outside, right, is a remote control button, and the mountain opens up like that when you come in.
We don't have that, but we do have a turntable at the far end, so that's pretty cool.
There you go. But what a place. I mean, tell us about it. So the stats are 2.7 kilometres long, you say?
Yeah, so it's
perfectly straight?
2.7 kilometres long, perfectly straight, 42 metre cross section, so pretty massive. Yeah. 6 and a bit metre road wide. A wide road, sorry. And yeah, it's all about a constant condition. So the temperature in here is practically 10.5 degrees all year round. Yeah. Even when it's minus 4 degrees, like it's raining out there today.
So very repeatable for testing.
Repeatable and the same every time you come.
Okay. And when was this place built? Because it's a juxtaposition of like 21st century technology you've put into something that was built, what, at the turn of the century, last century?
Yeah, built by the Victorians and commissioned and decommissioned in 66.
Right, so you were open how many years ago?
2014 the idea came to life and we opened properly.
Actually, just rewind there. How did this idea come to life? Because it's a bit nuts. I mean, did you discover the tunnel and go, this is a great tunnel I found, this would be really cool? Or did you have the idea first and then have to find a tunnel?
So not my idea, it was our MD or the group boss, Rob Lewis's idea. He wanted to create a really controlled environment so we could validate all of our simulation work by what we're going to be doing with the Beetle. Yep. And so he went about looking for a disused railway tunnel that we could use. We were based in Brackley at the time, and
So
this
not too
was
far away.
20 minutes away,
Yeah.
and the longest and straightest that was available. So we came to look around when it was still flooded. There were sheep outside where we were just there in the workshop,
Yeah.
and looked at a long journey from then, probably about 6 years until we opened, of trying to buy the place, trying to get plan permission.
So the idea came first,
Yeah.
then you found the place, then you had to make it happen.
Yeah.
And you've been open quite a few years now. What sort of cars have you come through? Give us like top trumps for everybody out there. What's the fastest? Because that's what I'm interested in.
Everyone wants to know how fast you
has
go.
somebody driven down here?
So most of the motorsport cars are going about 240 kph. That's not topped out, but
In
about
a tunnel?
Exactly, yeah.
What's that in miles per hour?
It's about 160 miles an hour.
That's insane.
So, and that's not topped out. That's just realistically, you don't need to go much faster than that to gather the data that you need.
So that's just cruising.
Yeah, just cruising. So, and that gives you plenty of time. So cars accelerate, then stay at that constant speed for a bit. They gather some data in that controlled flat environment, and then they...
So they stay at that terminal velocity, or 160 miles an hour, whatever it is, for how long before
Maybe
they need
10
to start braking?
seconds, 10 seconds
That's
at that speed.
Wow.
And then start what we call a coast down. So if you kick it into neutral and you watch the speed come off,
Yeah.
the faster it comes off means there's more resistance. And so we can make a decision just without any instruments, just by kicking it into neutral.
So they're not just looking at aerodynamics in a place like this. They're also looking at like cooling efficiency, because they can have repeatability of temperatures. So there's a lot of other things they're doing as well as just aerodynamics.
Yeah, so like some of the stuff we're going to be doing with your vehicle, we don't want to overcool the car. We want the cooling to be just right. So it's a bit Goldilocks-like.
Yeah.
If we've got too much cooling, then it means we're taking more energy out of the flow to cool fluids, liquids that we don't need.
Yeah.
So we want just the right amount of cooling so that we don't use drag effectively to make cooling.
Yeah, I need lots of cooling because I'm going up a mile vertical hill in the States, and apparently cooling's a big thing on that race. But aerodynamics is the one I'm mostly worried about today. So can we go back in and have a chat with somebody on the aerodynamics?
Yeah, let's go introduce you to Henry.
Brilliant. Right, walking back now, I've just noticed what we're standing on. Is this one of those turntables you were talking about before?
Yeah, so we've got a turntable here and a turntable 2.7 kilometres in that direction. Customers typically do a test out, turn around on the turntable, shoot back to get data in both directions, and we average over both.
No handbrake turns at the end.
No handbrake turns and no Austin Powers 3-point turns either.
Oh, well, I'll tell you what, you got some pretty cool stuff here, but we've got some cool stuff from our sponsors today as well, TE Connectivity. So back to the lab to show you some of them. Now, if there's one company out there that allows us to join all the dots as far as our conversions are concerned, it's TE Connectivity. Now, not only do they do things like contactors, which are obviously essential for our electric conversions, but their connector range and the variety and different types of connectors is vast. And we use a lot of different types of connectors from TE Connectivity, and they have a lot of different brands as well, like Deutsch, Ampseal, etc. And these are Deutsch ones, so these ones we use for bulkhead connectors, go up to a lot of number of pins in there. That's another type of Deutsch connector that we use there. They even do the connectors to allow us to connect to the Tesla motors as well, which is what that is there. And you can see here, in fact behind me, there's a loom getting made up on a loom board, and this is kind of one of the end results. It's not quite finished yet, but I've just nabbed it off the loom board because that has also some of their connectors on here. There's some Deutsch connectors there, and that's a 35 pin connector there. But some of the products that we use actually, like this DC to DC converter, already come with TE connectors on as well, or TE Connectivity connectors. So we actually have to connect in there for the high voltage, orange obviously. Low voltage, this has got a Super Seal connector on. There's a number of different Super Seal connectors here as well. Now don't forget, whenever you're buying connectors, you have to buy the right crimping tool as well. This is a crimping tool for these Deutsch connectors here, and it ensures you get a perfect crimp on those pins. The right tools for the right job, people. So there we go. There's a huge range available from TE Connectivity. This is just a small sample of the ones that we use here, all available from Mauser Electronics. And I'll put a link in the description where you can find those. But on that note, it's time to get back to the tunnel. New guy, Henry. How's Henry fit into this then?
So Henry leads our consultancy part of Catesby Projects. So we're here to do aerodynamics on your vehicle.
Yep.
Before we can do any simulation work, we have to get a proper computer model of it.
Yeah.
So we're going to scan it.
Okay.
So 3D scan the whole vehicle, and that's what Henry and his team are going to do for you.
Okay, so 3D scan the top of it, underneath, and anywhere else.
As many areas as possible.
Yeah.
We want to make sure that it's a really detailed model. So we want to scan the top side, the bottom side, and we also want to scan the inside of the car as well.
Awesome stuff. All right, so we're in Henry's hands for the rest of the day, are we?
That's it. Good luck.
Brilliant. Nice one. Cheers, John.
Cheers.
Right, Henry, you're going to have to explain what the guys are doing here, because we've just cleaned it and they've just ruined it by essentially creating a snow scene all over the car. Why?
Yeah, so the guys at the moment are spraying a white powder on the surface of the car, and that allows the 3D scanners to pick up the surface of the geometry with really good accuracy.
Right, so it's trying to prevent reflectivity or something like that?
Yeah, so it's just trying to reduce the reflections on the surface of the vehicle. The 3D scanners struggle with some of the reflections, so if we can eliminate the reflections, it means we can see the geometry in great detail.
Okay, so it's not paint then?
It's not. We're not painting your car.
Right, Henry, I've seen the boys have brought some pretty exciting looking tools. It looks like some of that Star Trek with some of the gun things they've got down there. Are there different stages of the 3D scanning process? Because they've got the thing on a tripod at the moment. So what's that, and what's the stages?
Yeah, that's right. So this is the Artec Ray scanner.
Okay.
So it's a laser-based scanner. It's primarily designed for architecture, but we're using it to kind of register the global position of the vehicle. So that's kind of stage one. So we'll place this scanner around the car to capture each side of the vehicle. And then we'll use the smaller handheld scanners to really get into
Those are the ray
detail.
guns I saw on the
Those
floor,
are the ray guns, yeah.
Okay, cool. Set to stun, hopefully.
Correct, yeah.
Right, Henry, looks like Ben's got the ray gun 3000 out. So what's this one do then?
So this is the Artec Leo scanner. So obviously it's handheld. So at the moment Ben is scanning kind of the front wheel and front fenders. It's using a kind of white light based scanner. And he's just capturing the local detail around that area.
I can see it appearing on the screen.
Yeah, that's right, yeah.
That's really cool. Oh wow. Okay, so that's which is more accurate and more detail oriented? Is it this one or that static
they're
one?
both just as accurate as each other.
Okay.
So that one is for the global position, and this one is to scan the local patches. We'll do lots of little patches around the car, and then we'll eventually stitch them up towards the end.
So they'll both meld together into
Correct,
one at the
exactly.
end. Wow,
Yeah.
that's going to be interesting. Cool. Henry, I think they want rid of us because they've turned the lights off. Why have they turned the lights off? What's going on there? What's the benefit of that?
So in order to capture the geometry, we want to make sure that there's minimal reflections. The reflections affect the accuracy of the scanner.
Which is where that spray stuff comes in again.
Exactly. So if we can turn down the lights, eliminates the reflections, and we can get very good quality scans.
Right, okay. And I saw on the ray gun thing, I don't know what it's called, I've forgotten already. On the screen, there was different colorations, green, red, yellows. What's that all about? What do the different colours represent?
Yeah, so green represents that you've got a good capture of the surface. Red means there's a little bit of uncertainty, and that's just essentially telling you that you need to scan that area in a little bit
so
more detail.
Ideally you want to get it to the point where it's all green.
All green, that's right, yeah.
Gotcha. Right, so we've raised up in the air, and the guys have 3D scanned the outside of it, but why is it up in the air?
So it's very important that we scan the underside of the vehicle. We expect the floor and the diffuser to be generating the majority of the downforce. So it's absolutely critical that we get the geometry of the floor and the diffuser with as much detail as we possibly can.
I'm glad you said that, because we put quite a bit of effort making sure that this is a flat floor. Normally these cars don't have a floor like this.
That's right, yes. So normally on most race cars the floor is flat, and looking at the floor I think you've made a really good start.
Good job guys back in the workshop.
The reason why it is flat is because we want to make sure that the flow is undisturbed. We want nice clean flow underneath the vehicle, so that it can get to the diffuser, and the diffuser can generate as much downforce as possible.
Awesome stuff. All right, so I'll let the guys scan underneath then.
Excellent.
Now we've got the camera up in the air, I want to talk a little bit about this, because on most race cars you see out there, you'll have a diffuser, which is what this is. But what's not clear to a lot of people, including me really, is what does a diffuser do and how does it do it? So Henry, you're the expert, you're the aerodynamicist. How does this thing work? What's the benefit?
So we've got the diffuser at the back of the car, which is this black section here. You can see that it's angled slightly upwards, and that is to help accelerate the flow as the flow reaches the underfloor to the back of the diffuser, and then that speeds up the flow, and that creates low suction pressure around the kick point, and that's the reason why it generates downforce. So
low air pressure here essentially is kind of sucking the car to the ground then, yeah?
That's correct, yes. You can also see that we've got what's called diffuser strakes.
Yeah.
So
these flat bits here that are 90 degree.
Exactly, the fins that are kind of pointing straight down.
What are they called? They're called
diffuser strakes.
Strakes.
Strakes, yes.
I've learned something today.
So again, the idea of these strakes is that they help to spin vortices, which are kind of a bit like mini tornadoes.
Okay.
So they generate low suction pressure and help draw in more flow into the diffuser, and it enhances the effect.
Awesome stuff. Right, there's a test on this later, boys and girls. As an engineer, I am intrigued as to how this actually works, because I've seen it appearing on the screen, but how does it actually work? I mean, what's the mechanics behind it?
Yeah, so this is the Artec Ray 2 scanner. So it works by pulsing a laser out of a source, and then that hits a rotating mirror, which sends the laser into all sorts of different positions, and then it's clever enough to receive the laser signals back, and from that it can generate the geometry of the vehicle.
So when the laser comes back, it can actually calculate what that distance was from where it hit?
Precisely, yeah.
Insane. I can see the mirror spinning around. That's spinning at some rate of knots, isn't it?
Yeah, I'm not quite sure how fast it's spinning, but it's probably a few hundred RPM. Yeah.
But how accurate is this when it's doing all this?
So this is probably accurate to about 1 to 2 millimeters, but in terms of the global accuracy, that's what we're trying to capture at the moment.
Yeah, I've seen they've been moving it around different positions throughout the day so far, just to, now it's raised up as well, so they're doing the same underneath. But with the handheld ones are even more accurate, you were saying?
Yeah, the handheld Leo scanners are accurate to 0.2 millimeters.
That's insane.
So we'll go around the vehicle and scan local patches, and then at the end we'll combine the global scan with the local patches, and that will give us a really nice accurate geometry.
I wish my car was that accurate. Now, Henry, I've seen this slowly appearing on the screen in the corner, and it's getting fairly complete. So can you explain now what we're seeing in front of us?
Yep, so we've just read in the data from the Artec Ray.
That's the one on the tripod, the static one.
Correct, yes. So this is the one that should give us a really accurate global position.
Yep.
It's a little bit fuzzy at the moment, but that doesn't matter. We've not patched in the scans from the Leo, so we're going to do that afterwards.
Ray guns, yeah.
Exactly, yeah. So here we can just see that obviously it's a digital model of the vehicle that we've scanned.
Yeah.
And then if I flick onto this screen, hopefully that should give you an idea of the quality that we get from the Leo scanner. So you can see that it's picked up all the colours and the textures, but most importantly, it's looking a lot nicer.
Most importantly, the sponsors. Thanks, Henry. So you can move all that around in virtual reality?
Yeah, so you can move that around, pan it around, spin it, so you can see the level of detail that we've managed to get on the model. So it's a really nice, accurate, highly detailed piece of geometry that's going to be perfect for CFD.
And putting it in Forza. Any gamers out there? That's the car you want to race. Right, let's have a chat on the real car, because I'm interested now we're starting to put the model together in virtual reality world.
Yep.
I want to have a little bit of chat with you as to what you think is going to be the easy wins, if you like, on the car. So let's have a chat about that.
Let's do it.
Right, so Henry, I've seen what's appeared on the screen there, but that's not finished though, is it? I mean, there's a lot of fine tuning on that to do.
Yeah, so that's not the final product. So we're going to take the data, we're going to go back to base, and we're going to process the model.
Yep. So
that's going to involve making sure that the geometry is watertight, it's defeatured, it's simplified, and a whole bunch of other things, so that it's compliant with our CFD solver. And that's going to take probably 2 to 3 weeks to turn around.
2 to 3 weeks?
Yes. Now,
Tim knows I'm a very patient man, don't you? So So what do you think, like fast forward 2 to 3 weeks,
Yep.
you know, you're an experienced aerodynamicist, what do you think are going to be the challenges
Yep.
and the easy wins or things you've got to take into consideration with the car in front of you here now?
Yeah, so I think there's going to be 3 main challenges.
Okay.
The
Only
first,
3? That's a good start. Good, yeah. I thought there'd be about 10.
The first challenge is going to be generating enough downforce from the underfloor, the splitter, the diffuser, and the rear wing, such that it counteracts the amount of lift that we expect to be generated from the bodywork. So
There will be a lot of lift.
there's going to be a lot of lift being generated from the roof, from the bonnet, and probably from the front and rear fenders as well.
It's completely the wrong shape for a race car, isn't it? With that curve like that.
Very curvy at the top.
That's why I went
yes.
big with the rear wing.
Yes, I see.
So, you know, we've got some big tools to help
Yep.
you with the downforce. So yeah, downforce is challenge number 1
Challenge
to
number
counteract
1.
the lift of the body.
Correct. Challenge number 2 is it's all well and good generating that downforce, but we need to make sure that that downforce is well balanced. So making sure that there is a good proportion of downforce acting between the front wheels and the rear wheel. So probably something of the order of 50% balance or maybe 40% error balance.
Okay, and how do you achieve something like that?
So we are probably wanting to create a splitter at the front. We're obviously going to be generating quite a lot of downforce from this rear wing. We've also got a diffuser, which is generating downforce, so we need something at the front to counteract that balance.
Because otherwise the car's going to be pushing down like that and the front's going to be coming out, so we need that splitter on the front to balance it all out. Okay, cool. So that's number 2.
That's number 2.
Did you have a third one?
And then challenge number 3 is going to be making sure that aero balance doesn't change too much when the vehicle is under different conditions. So if the car's braking, in cornering, we want to make sure that that aero balance doesn't shift too far forwards or too far rearwards to make sure that it's a nice handling vehicle.
Okay, cool. So lots to be getting on with then.
Yes.
Cool. I can't wait to see the results, Henry. Thank you so much for today, and I wish you luck with the computer analysis side of things, and we'll probably pop back and do a conclusion episode to go over the results.
Yeah, excellent. Can't wait to see the results.
Nice one.
Cheers, Richard. Cheers.
All right, boys and girls, that's it for this episode. It just remains for me to thank our sponsors, Mauser Electronics, and the sponsor of this episode, TE Connectivity. Go to mauser.com for any of your electronic components needs. And massive thanks to John and his team at Catesby Projects, but also Catesby Tunnel, because I've been itching to actually have a drive up this tunnel, and John has kindly allowed me to do it. Not in the race car, certainly not until the aero's finished, that's for sure. But we're going to go for a spin up and back in the Lander, yeah?
Sounds good. Let's have a look.
Right, I'll see you in the next one, boys. We're off in the tunnel.
Slowly onto the turntable.